Morning. It's the last class for us, but as I tell to my regular research students, once an NM cadet, you're always an NM cadet. So you're part of our family, academic family. So feel free to get in touch with us whenever you think we could be of any utility to you, or you could be of utility to us, or we as a team could do something better for the world. Okay. So I really, as I said in my last lecture day before yesterday, thoroughly enjoyed teaching y'all, and hope you at least enjoyed half of what I enjoyed in teaching you. Because throughout my career, I felt that teaching is the best way to learn. So I've attempted to learn from you all, from the kind of questions you ask, the kind of inputs you give me when I ask you questions. So it gives us different perspectives, and when we look at it from that way, we learn a lot more. And these 2 days have been very special for me. The last lecture which I had on Monday, that was my daughter's birthday, and today happens to be my dad's birth anniversary. So both were great celebrations at home. So I'm in a celebratory mood, and I'm sure even if this goes for a little long because you have 2.5 assignments here, I'm sure it will be a celebration. And time is more than the actual duration from start to stop. It's in our experience of time. So if we are happy, we find that the time moves much faster. And if we are sad or bored or angry with something, then we see that even a short time seems like a longer duration. The rules remain the same for all your homeworks. So whether it's the last one or anything else, just that the weightage is different because the complexity or the difficulty levels are a little more. But this is a team game. I was your coach, so coach take the back seat when the game starts. So it's your game. Make it as enjoyable for the audience as possible. Okay. So there you go.
Just one second.
Yeah.
Before I have something really special for you, for
Wow.
our coach. I brought this specially from America. I know you're a big
That's so.
fan of
That's so.
chemicals.
Oh, that's so wonderful.
So, this is for you. Thank you
This
for teaching
this
us.
means a lot. Akshardham.
Yes, thank
It's
you
a
for teaching
beautiful,
us last
beautiful.
5
It's a
years.
real
Thank you very
pleasure.
much.
Dirgha Aishman Bhava, Vidyavan Bhava, Kalavan Bhava, Sakla Arogya, Aishwarya Prapti Rastu, and that holds for everybody.
Yeah.
Thank you so much.
Thank you very
Really
much for teaching us.
appreciate it. Really appreciate it. Thanks.
So one small addition.
Yeah.
Today is certificate.
Exactly. Yeah, that's true. That's true. So, which is why you have the Ganesha over here.
Yes.
Even though it might be difficult to decipher because it's inverted. Because it's supposed to be the Mooladhara Murti going to Shiva, which is a Sahasrara. Okay, so you get going. Thank you. And as I just reminded at the end of last class, I want you all to participate. Whoever is presenting doesn't matter. And don't skip steps. Even if it's a simple problem, go step by step. Of course, there are many ways of answering the same problem. There's no one correct way. So you can get to the same solution by different paths. Some prefer to touch the nose this way. Some prefer to touch it this way. So it doesn't matter. It might only increase the time, etc. But whatever procedure you use, I'm okay with it. Just make sure that you go step by step. And if I want everybody to be kind of involved, I know you have a lot of distractions like mobile phones and laptops and tablets, etc. That was okay when I was teaching, but it's your teammate who's doing it. And for a game to be enjoyable, it's important for everybody to be involved in the team. Okay, so I just want you to make sure that if they miss a step or miss a notation or something, just shout out to them. You're like cheerleaders, whoever is here, right? Thank you.
Okay, so our first question of the day. We have a cylinder, a hollow cylinder rolling down a hill. The hill's on an incline. So here is my drawing of it. You can see it's tilted at an angle of 53 degrees. And so then I in turn tilted my coordinate axis. So now it's like, instead of being normal, it's tilted. That means that our mg will have two components, our gravity, but our friction and our normal force will only have one. And so then the givens are just mass is m and radius is r. And so I started by doing sum of forces in the x direction is equal to mg sine of phi, and then minus friction, which I just called little f here. And we know that this is equal to mx double dot c. And so then to do the next step, I did sum of moments, z. That is equal to the moment of inertia times theta double dot. And then that is equal to mr squared theta double dot. And then the sum of moments is also equal to friction r. So out of that, you can get that friction is equal to mr theta double dot. Off that, you know the definition of x double dot c is equal to r theta double dot in the I hat. And so then going back up to this, we know that the sum of m of x, so m r theta double dot is equal to mg phi minus r theta double dot. So then our masses cancel out, and we can get theta double dot in terms of r and g, so g sine of phi
If it's not visible,
over
you can go to the other side and take it. That's what I was mentioning. You can
to
carry
r.
it and go to.
And then you need to plug that in to the original kinematics. So delta phi is equal to, this is actually delta theta. T squared. We're given that it starts at stationary, so the initial velocity is 0. D over 1/2 of theta dot t squared. We're solving for time on this one. So you get 4d g sine phi. And that is equal to our answer, 2.99 seconds. Teammates, do you have any additions? Am I forgetting any little arrows over my vectors? I would think that's where I'd mess up. Inertial. Okay. Oh, I got one more question.
It's a great opening innings. Let's see the rest of the batters. How you do?
Okay, for this one, again, we have the same situation where we have, my pen is dying. Thank you. We have a ball on an incline. We have gravity pointing down. Friction is pointing up, and Fn. And so then I'm going to approach this the same way where I tilt my coordinate axes. So y, j hat, I hat, positive. Our angle here is 51 degrees. Our coefficient of friction, mu, is 0.17.
Take turns with you.
Mass is 10 kilograms. Oh, and I had an inertial frame. Okay, I already wrote it.
You probably go there so you can get everything covered better. get into the corner.
Okay, so this one, I started with sum of forces. And first the y direction, that is our Fn, our normal force, is equal to, or mg cos theta. Did I call this one theta? Yeah. Equals 0 because we're not like moving up or down. We're staying in the same plane in the y, so you're not accelerating in it. So that just gives us force normal is equal to mg cos theta. And sum of forces in the x is equal to mg sine theta minus friction. We know friction is mu Fn, and we know that this is what is giving us our acceleration. So ma, and that's our translational acceleration. Then plugging those in, all the m's cancel out. Coefficient. Yeah. And then A is equal to G. Five, 2 meters per second squared. Then we plug it back into the original equation, so we have velocity in the I final is equal to velocity initial and plus A delta T. We're also given that this one is at rest, so our initial velocity is 0. And then that gives us that our final velocity is going to be equal to 6.522 t. And plugging that into the x equation, x final is going to be x initial plus VI over 2 delta t. And we know, like, our position, we can just kind of say 0, because you're just finding the total distance traveled, not like from what origin. And we also know that our velocity initial. And so off that, we get that the square root of 9 over 3.5, or 3.279, 2759 is equal to delta t. Are my units wrong on this? 1.655. Calculate the time required. Okay, seconds. That's what I got. I just wrote it in meters per second in my notes. Okay, Lolita, you're going.
Just use this chair. You can feel comfortable here.
So for number 6, we're given that a particle A of a certain mass is moving at a given velocity vector, and we are also given the mass and velocity of particle B. We're asked to calculate the linear momentum. So this is mostly going to be governed by P equals mv, where P and V are both vectors and m is a scalar. So this problem should be relatively simple. We are going off of an inertial reference frame. And that's because the observer is stationary while this is occurring. But they don't really give us a position vector or anything. We don't know where they're starting off. It's just the momentum of the system, both particles. So what we can do in this case is add the momentum or the linear momentum of each particle and then combine it, and that will be the total momentum of the system. So I'll write that down. P total equals I'll make this A and B. So, yeah, we can basically just plug this in. So we have 5 times velocity vector 9I plus 9J plus 6 kilograms. And this would be meters per second. And now I'll do this in a different color, but we basically have these 2I and only one component in J, so we can just add it. 45 minus 24, which is so that would be the total momentum in vector form. And we're asked to find the linear momentum only in the x direction. So for that, we would just take the x component of this vector. So the final answer, px equals 21 kilogram meters per second in the I hat direction, which, yeah, just means it's in the x direction. So that's that problem. And then for the next problem, can I erase this? So for this problem, we are given, again, a particle, a mass, mass, 7 kilograms, and we're given the velocity. That's a vector, velocity vector. And we're given the same for B. So I'll just write down all the givens here. And we're also given in this situation that the two particles are colliding. So we have to make the assumption that this is a perfectly elastic collision, and all momentum is conserved and none is lost as heat or sound or anything. So yeah, we aren't given any other information in order to calculate it otherwise. That's why we're making that assumption. And so we're given the mass, the initial velocity, and the final velocity. So again, we're also assuming that mass does not change in this problem due to the collision. So let me just draw out the problem here. So you have particle A and particle B. And then after, so this is in the beginning, and then after, denoting as 1 and 2, the two particles. The two particles are together. And then after that, so that's during the collision, and then after the collision, they're going off in their separate ways. So A would presumably be going in that direction, and B might be going in that direction. We don't really know, but we're about to find out. So let me just put in arrows here. Sorry, that's kind of close together, but oh yeah, and this is the inertial frame of reference. Should have added that. So we have to calculate the change in the x component of the linear momentum, which again we could find the total momentum and then just take the x component of that total vector. So, I forgot to write down the final velocity. So this is 1, so during the, or before the collision, so I'll denote that as 1. And we also have VA2 and VB2. Oh. Alright, so I'm going to write down the same formula that I did before. P equals mv, or actually in this case it would be the sum of mv, but yeah. So for this case, P total would be equal to MA VA plus MB VB. And this is true for both, this is true for both the initial and the final conditions. Because we're assuming that it's perfectly inelastic, we aren't losing any momentum. So P total 1 equals, I should have written 3 since I put 3 there. P total 1 equals P total 3. And that's technically also equal to P total 2 at the instant of collision as well. But for our cases, we only care about this part of the equation. So I'm just going to plug everything into this. So we're first going to find the momentum at, the momentum at 1. Oh yeah, sorry. I would like to say, so we already, because we're assuming that it's a perfectly inelastic collision, we know that there isn't going to be a change in momentum, so the x component would be 0. But I'm going to run through the entire formula anyways, just to prove that it is 0. So 7 kilograms times VA, so 3I 3J, which is 21I 21J kilogram meters per second. So that would be it for 1, and we could theoretically simplify this. And then for 2, it would be 7 kilograms negative 3 root 2 3. So we can see here that if we equate, sorry, I keep writing 2. If we equate 1 and 3, we can clearly see that these two I components will cancel out, and these two I components will also cancel out because they're the same and they will be on either side. So essentially, the J components also do cancel out. So we can say that the change in the X component of the linear momentum will be 0.
So there are motors here, so you have to hold this and just switch it off and on. You can leave it. Leave it. Just leave it. Leave it.
Yep.
You hold this. Okay. Here there are motors, 3 motors. So if you hold that, then it will go off.
Yes, I did. Okay. So in this question, we're given velocity as a function of time in the expression v equals t cubed in the I direction plus t squared in the j component plus t in the k component. And where I and j, k are all unit vectors, the direction are affected in frame h. And so I guess we can draw that out. So in frame h, we're given vectors that are given in x or I, j, and k. So we can just draw those as our normal actual triad, where it's like x, y, I, j, and z, k. And so we're given a function describing the velocity in this frame. We're also given that the angular velocity of h, so the frame h, in a second frame called r, is given as omega h to r. So if we want to draw another frame, it would basically be, we can draw it just as r, and we'll draw it sort of in the same direction, but we'll note that h itself is going to be moving in some sort of angular direction in respect to this frame r. So we'll call it something else. x1, I1, z1, and k1. So we have two frames. In one case, it's rotating. In the other case, we're keeping it still. And we're asked to find the magnitude of the derivative of velocity in frame R at a given time of 1.2 seconds. And so we're given an equation in class. We can relate differentiation in two different frames of references as we have here, where the general equation is given as dq, where q is just any sort of vector. It can be displacement, it can be velocity. In this case, it will be velocity. And so we just plug in for q here as velocity, and we'll be able to relate the two different frames in order to get a proper answer. So if we want to follow the same sort of format here, we're solving for the velocity in frame R. So then on the left side, instead of having I dq dt, we'll have r v dot, because we're looking for the derivative of velocity, so it's going to end up being acceleration, is going to be equal to a dq over dt, which is going to be in our h frame, same sort of velocity component, and plus omega that we're given. So omega, I believe it's h to r, so it's h to r. And we're going to cross this with q, where q is going to be in our original reference frame, so which is h. Okay, so based off this, we already know pretty much all the terms on the right side. So we're given velocity in h. We're told what omega h to r is going to be, and then velocity in h, I think we were also given. Velocity h we were also given. Yeah. That's the same sort of velocity that we had, that we're taking the derivative of. We're just keeping it as it is in the first place. So if we want to write this out in terms of what we have, r v dot is going to be equal to the derivative of velocity in the h. So that's going to be our whole function here, where it's t cubed, t squared, and tk. So if we want to take the derivative of that, it's going to end up being 3t squared in the I component, plus 2t in the j component, plus 1 in the k component. And that's just directly just taking the derivative of what the velocity was in the h reference frame. Then we can add this with the cross product between...
I'd just like to mention that v is an arbitrary vector. It's not the velocity.
It's
If
not
it's the velocity, then you would not say velocity of a body, right? So you write velocity is always of a point on the body. So you're saying vr or vh, it's of the body, right? So it's with respect to that frame is what you're saying.
Yes.
But v is just a vector, okay? So even though we normally use v for velocity, it's just any arbitrary vector for which that equation is valid.
So you're saying that we don't have to label like the frames of reference?
We should, but you should not call it velocity.
Okay.
If you call it velocity, then you have to put a subscript of a point associated
so it's just
with
gonna
that.
be an
So
arbitrary
the velocity is
vector.
of that point.
Okay. So then,
So whenever you just say a rigid body and a velocity doesn't have any meaning.
okay. So then talking about this vector, we're going to take the cross product between angular velocity, which we're told is t in the I direction, t squared in the j direction, and t cubed in the k direction. So if we just write out this cross product, we'll have I, j, k. We're given what omega is as t squared, and t cubed, as we're given the arbitrary vector v in the h reference frame. We're told what this is as t cubed, t squared, and t. And so we can take this this cross product right here, which will give us about, well, I guess I'll just write it out. So bringing everything down, we have that this 3t, this whole sort of thing will come down. So we'll have 3t squared. I guess I should just do it. Taking this cross product right here, it'll be t squared times t, so t cubed, minus t to the 5th in the I direction, minus For the j, we're doing the cross product, so it's going to be t squared minus t to the 6th, the j component, plus our k component, which is going to be t cubed again, minus t to the 5th. That's basically just the result of this cross product. And so now that we know these two, we can combine them into one entire term, where I'll just take out common factors. So it'll be 3t squared plus, we'll add up the different components, so the I components will be 3t squared plus t cubed minus t to the 5th. That's just all our I different components combined, plus 2t minus t squared plus t to the 6th, j plus 1 plus t cubed minus t to the 5th, and our k component. So that's just us adding up the two vectors together. We're adding up all each component, and we're bringing them together. So this should have been I. And we're actually given the time here. So plugging in time of 1.2 here will give us an answer. Will give us the velocity being, or like not the velocity, the derivative of the arbitrary vector v as 3.56 in the I component plus 3.95 in the j component plus 0.240 in the k component. Now I believe we're actually asked for the magnitude of this derivative, and so in order to do that, we just take the square root and square each different term in it. So 5/6 squared plus 3.95 squared plus 0.240 squared. And this will give us a final answer of about 5.3197. And since this is an arbitrary vector, we can't necessarily get... actually, can we not say it's velocity? Because we're given units of meters per second.
Sure, you can call it velocity, but if you call it velocity, then you have to mention of which point.
Okay.
Because there's notations that you have. This is okay to put the dot over there because you're
So
taking the
respect to
time
time.
derivative with respect to r, time derivative with respect to h, time derivative with respect to h, right?
Yes.
But, sorry, this should not be dot. The dot should be on this.
On this one? It should be on this one.
Oh yeah, this is omega cross. Okay,
Yeah.
right. So that's fine. So here you don't need a h then.
Because
Yeah,
Okay.
because it's just a v by itself. So you're right that from the unit we can guess it is the velocity. But whenever we write the velocity notation, it has to be of a particular point. So remember, always angular velocities are of rigid bodies or frames,
Yes.
and
So
velocities
velocity
are always of a
point.
point. It could be a point associated with the rigid body, but it has to be a point.
And so then if we were going to bring down our units, so we're taking respect to, we know the initial units, we're going vector v as meters per second. We take the derivative with respect to time, we know the new units will be meters per second squared, and so when we bring that down, our final answer will be in terms of meters per second squared. And that's our final answer of 5.317917.
Whose presentation? No, she proved. No, she showed that both are equal to each other. The difference is therefore 0. She got an expression for the initial momentum and the final momentum and showed that
Okay,
they're exactly
so
the same.
I have the next question, which is where we're looking at this sort of antenna device, and I'm going to sketch it out, at least make a sort of simplified sketch. This is our coordinate axes. And we have, what we know is that we have a rotation around the y-axis. We have a rotation about the z-axis. going this way. And then we have another one that is going in this direction, which they call x2. And we want to know what the magnitude of the angular velocity about the reference frames is, I think, what's the most confusing part of this problem, but it's sort of like we have a couple intermediate reference frames. So this first velocity is about the intermediate reference frame J2 over J. No, wait. It is J1 over G. This one is J2 over J1.
Yeah, rather than over, you would want to call it with respect to.
Well.
Yeah, you write it that way, but
I see.
you will call it as with respect to rather than over.
Okay. So this is about A with respect to J2? Okay. So we want to find the angular velocity of A with respect to G. That makes more sense. Okay. So we have a formula that from class where we can say that the the angular velocity of A with respect to G is equal to the sum because angular velocity is additive. We can say it's equivalent to the sum of all the intermediate reference frames. So our expression becomes this. And another thing that we know is that this intermediate reference frame along x2 is dependent on an angle. Is this is phi or phi? Okay.
You're right.
And we know that phi is dependent on time, as it says. Phi is a function of time, and we're given a time. We want to find this magnitude at a time equal to pi over 2. So I guess we could additionally write this as like so, because with respect to time. But we need to know that these two reference frames of G and J1, or rather these two axes are fixed with respect to time. This is the only axis that is changing. So these two would stay the same. And so the question is that we need to try and represent this angular velocity in the same reference frame as the rest of these. And so I think the easiest way to do that is if we shift the coordinate axes this way. So here are our original ones. We see that there was, well, this was the angle of phi that was taken. And at pi over 2, we would know that this axis would go in the j direction of our original reference frame. I'll call this reference frame A, and this is reference frame B. So at time pi equals 2, in the reference frame A, this vector would be in the j hat direction. So that means we can express both of these, so the angular velocity of J1 with respect to G and the angular velocity of A with respect to J2 can both be represented as being in the J direction for this time at pi over 2, which helps make the math a little bit easier. So putting in the now the actual expression, the actual vectors for these angular velocities, we know that the angular velocity of A with respect to J2 is 4t in the J direction. So I can say that J2 over J1, that is in the k hat direction, and that is 2t squared. I think did I put the wrong one? I think I put the wrong. J2 over J1 is 1. That's the one that's in the k direction. Okay. This was
How's the
A over
angular
G.
velocity of A in J2 along J hat? J hat is given to be parallel to Y, right?
Yes.
Yeah.
So I might not have thought this the right way, but my thought was because this reference frame is dependent on the this angle phi, and angle phi is a function of time. So as angle phi is changing, at pi over 2, the angle would be pi over 2. So it would align with the y, and j hat is perpendicular to y. So we would know that it'd be going in the same direction as the. I guess it's not entirely right, but I don't know if there's the right way to explain it, but that's kind of how I thought about it.
Yeah, at a particular instant it might turn out to be that, but what you're writing is a more generic expression, right? So you should have a
Right.
unit vector introduced along x2 direction, which is a function of j hat and I hat, right?
Okay.
And at maybe at the time of interest it does become parallel to j hat, we don't know,
Right.
but we are not yet there.
So I don't think I wrote a generic expression. So how would I formulate that?
So it's just that particular direction which you've already drawn, right? So it's your x2.
Right.
So to have a unit vector in that direction, you'll have to go cosine phi along I hat and a
Right.
sine phi along j hat.
Okay.
That's
right.
it, yeah.
Okay. So this would be then. This would be along, like cosine. Okay, I think I understand that. Okay, let me do. And then again, we know that the angular velocity J2 with respect to J1 and angular velocity J1 with respect to G are fixed in both intermediate frames of references. So we can say that those are both staying along their respective axes and they're not changing with respect to time. Okay. So I guess that would be my, and this is all in the frame of reference of A. So I suppose that would be my generalized expression. And then at pi equals 2, at t equals pi over 2, we would then be able to make the following substitutions. So
no, it's not in the frame of reference A. You already have that already written. It's in the frame of reference G.
oh, I see. Okay.
So it's two alternate ways of writing it. Either you can put /G or you can put a GS. So what you're
I
writing
understand.
already is
Okay.
fine.
So if I
Because if you write angular velocity of A in A, it would be 0.
right. So if I put in now pi over 2 for this phi expression, the cosine of pi over 2 would be 0, and sine of pi over 2 would be 1. So
So that t on the left hand side would be 0 then on that equation, the equation that you're just writing right now.
t would be 0.
Because you're
I
taking for a special
think
value of phi, right? So
right. Yes. Okay.
no, you're given phi equal to 0 only at t equal to 0,
Right.
right?
So then I guess
Not
we should.
at pi
It's
by
better to
2,
write
right?
out the.
You want to determine what it is at
Function?
pi by 2, but
So
what is given to you initially is at t equal to 0.
if the structure is in the. Well, that means you can write a function for between t and phi. So I guess this would be the function. At least I don't know. Maybe you can't make that assumption, but am I wrong in saying that?
It depends on the value of the angular velocities that are there, right? So you've been given omega j of A in J2, right? And similarly, you have J2 in J1. But what you're looking at here is of J1 in, no, you're looking at phi, right? So
Yeah.
phi is of A with respect to J2, right? So it should come as part of that. So you have to correlate your omegas with your phi dot. So which omega is equal to phi dot?
I don't think I really understand what that means.
Can I offer a suggestion?
Sure.
So phi is the angle of rotation of J2 with respect to J1, right?
Yes.
So then maybe your phi dot would be your omega J2 with respect to J1. And then you can figure out how far, based on the angular velocity, you can integrate it to find what the we'll figure out how far phi has changed at the time that you're interested in.
Do I need to know that though? I'm not sure why I need to know that.
Because well, we don't know because the velocities are changing. We don't know what phi is at time equals pi over 2.
Okay, sure.
And that depends on how fast the angular velocity of J2 with respect to J1 is, right?
Okay.
But that value is equal to 1.
Yeah.
So then when you integrate it, it's going to be t.
Right, okay.
So if you just wanted to write that out, it would just be phi of t is equal to the integration of your omega j2 over j1. Always for j1.
So then your initial assumption that phi would be equal to pi over 2
Right.
is right.
I hope she's all right. Can you? Maybe. Yeah, if anyone thinks that they can finish it, then go ahead. Yeah.
Given that omega j2 with respect to j1 is 1, so when you integrate 1 with respect to t, you do end up getting 5t is going to be equal to t, which we can actually check with what we're given in the problem. We're told that phi at time 0 gets you a phi of 0. So I guess we're just checking that. So when we're plugging in t into our phi equation, we can put it back into our sort of omega here, where we said it was related to that. So
this is correct, right?
I believe so.
So we know that angular velocity, magnitude.
I'm not gonna get points off now. I'm gonna get points off.
You're getting out for your phi.
It's supposed to be a team thing. You can jump in on one of my questions, okay? Just chill out here.
You can also write omega of A with respect to J2 as an actual rate.
I don't.
because we know
I haven't looked at your
phi
problem. I guess I could take a look. I solved it. I don't know what I did, but I thought through it a certain way, but the way I thought through it was wrong. I don't know, it's just wrong. So now I need to do these extra steps to determine it, but I didn't do those extra steps.
Yeah. No, it's fine.
It feels a little excessive. I don't know.
Yeah. Giving me deja vu from like him grilling me about what frame of reference we're in. I'm like,
Yeah.
it's okay. Do you want to just like,
Okay.
do you want to come back to you or? Because like you could take some extra time for your problem and in the meantime. If that makes you feel better.
So we're saying 4 times
I guess so, but
Finish the problem and then you can jump in on mine. I want it. really get 10, we could be counting it.
Plug in T right there. Okay.
It looks like the units. The units.
I should just finish it. I should just finish it. But
I mean, go downstairs to the bathroom, like wash your face, freshen up a little bit.
yeah, I don't have my key. No, I need to just do it. As soon as it's done, it'll be fine. Yeah, I should just finish it. I just wish they didn't have the camera up in my face. I mean, that'd be really cool, but it is what it is. Okay.
I think they're doing it right now. I think they're trying to do it right now. Yeah, so jump in on mine, okay? Don't worry about it. Just go downstairs and wash your face and come back, okay?
I left my keys in there.
Huh?
I
No, near the reception.
Oh, okay. Number 4. Okay.
If you would, I think that is just
I could just have you write down a couple things.
as if your team is already.
I should just do my. I'll just do my. It's fine. It's okay. It's okay. It's okay.
You got a magnitude of 12.
You magnitude of 12. The answer should be about 11.26.
What did we?
Something
What did we miss?
Something is negative.
Should we look? Should we look
Oh,
at
you think the magnitude thing will be different?
Isn't that what it's asking for?
What are the other ones and minuses?
Yes, it's asking for the magnitude.
Okay.
Yeah.
Now, if you do the magnitude of that, you get. Well, we did it wrong. Oh, it's J hat.
It is J hat. You added up the 2 J hat components before squaring,
Yeah,
right?
So it's. Yeah. So that's right.
Okay.
So
BT, do you want to write the final answer?
Yeah. Just okay. So we have the vector glass for magnitude. So magnitude of omega would be at our it's going to be just the square root of this. We're squaring each component. So our J component is going to be 4 pi divided by 2, so it's just 2 pi. Plus this, which is 2 times pi over 4, so it's pi over 2. Plus our K component, so it's 1 squared. So we do this to get the final correct answer of 11.26. And this is still magnitude of angular velocity, so it's going to be 8%.
Yeah, of course. Right, so my question is a device simulating conditions in space allows rotations about an orthogonal axis as shown in the figure. So what we are basically finding the k component of the angular velocity at this specific time is just 3.9 seconds. So first, I'll draw the reference frames. There will be 3 reference frames that I've done for this. First is reference frame for this one. Alright, so first is with G. So pardon my drawing skills. This would be Z1, K1. This would be X1, I hat. This would be Y1, J hat. Then we have reference frame B.
Okay.
C. So this reference frame is a little different. So the original, I'll draw the original header, but this would be C2, Z1, K2 hat, K1 hat. In this case, this would be Y2, J2, yes, and this would be X2 hat. Sorry, I forgot to omega Z goes into this branch. And the second one, so the original reference frame is like this. If I draw it, even though we won't be needing it for this question, I'm just drawing it. It would be like similar to this, and for this, let's call this angle beta. And in this way here, omega x is going, and this would be 1. And then the last frame of reference that we use is, if you look kind of, and it's pretty much flipped, and in this direction where this. One second. So this is x3, x2, and C3 for A. And in here,
Yeah, you forgot my.
oh, sorry. I just realized it. So much peer pressure
Can
today.
one of you just keep a watch out when they use the microphone?
So here, if you see, this would be Z2, and this would be theta in this case, and missing it. Yes, and so would be the theta here, which is Y2, and this would be the theta, and here omega y is going this way. So now we have to find, so now we start looking at the k component, where to find it first, and you'll find it according to the b coordinate system. So that would be omega c by a. Or c by g. So g is ground and c is the rotational moving thing that's here. Omega c by a plus omega a by b.
plus
He's getting there, right? Where he's going.
omega.
You carry on.
Oh, okay. So here, oh, okay. Okay, so this would be
Sit
how.
there, Prashant. Just sit there comfortably and take.
Okay, yeah.
Sorry.
Am I blocking it too much?
No, please go ahead. No,
Okay.
No, it's okay, but it's not visible for you now.
no, it's okay. But the picture will get.
They will
the,
Yeah, the
yeah,
projector.
so the project.
Oh,
My heartbeat goes up whenever something like this happens. Little more.
Let
left.
let it be where it was. I think that was fine.
Yeah, this is fine.
We can cut this out.
No, it's fine. It can stay. Good content.
Right. It's part of the team's
Yes.
tactics, not strategy.
All right. Shall I continue?
Please.
Okay. So then, here finding CA would be the most complicated, but I'll just write down the equation now of all these three, where this would be omega y cos theta of j hat of 2 plus. Now I'll go this way and that will be blocked. Okay, let's see.
I think the original position was perfect there in the corner there
Okay.
for the chair, so you can get this side view from there.
Sin theta of
Yeah, once he finishes this
Yeah,
part, we can move
sure.
back.
2 plus omega x 2 plus omega of k2. So then this will continue as omega x I at 2 plus omega y cos theta j 2 plus omega z y theta k at yes. This is a be 2 2, right? So now we can find the theta as we're given time is 3.9 seconds, and we are also given w of omega of x. Sorry, not w of omega of x. So we can pretty much. So one thing that I want to make sure that we are also given that omega y rotation is.
Turn wherever the action is. Don't just keep wherever what he is showing you. Just focus on that.
Right,
Yeah.
I'll just turn this way then. Yeah. So it's one tip that we're given that omega y rotation is fixed axis in C and A and not in B. And this axis is parallel to y at t equal to 0. So that's why we can use theta exactly how we get it, or else we would have to add the angle that we were given. So now we look towards theta as we are given. So theta would be equal to 7 radians per second times 3.9 seconds is the time. So times 3.9 seconds canceled is equal to 23.4 radians. This is what you get as theta. And now it's just pretty much plug and chug into the formula that we have given here, where we'll put in the numbers where omega x is 7 radians, omega y is 6 radians, and omega z is also 6 radians. I'll just write it here on the side. It's easier. All right, so omega x is equal to 7 omega y, 6 omega z is all of them radians per second. So this would be equal to 7 I hat 2 plus 6 cosine of 23.4 j hat 2 j hat of 2 plus 6 plus 6 sine 23.4 k hat of 2. So now if we, excuse me, so now if we just solve all these together, we would get the equation, we would get it equal to 7 I hat 2 plus 5.506 j hat 2 plus 10.96 k hat of 2. So omega c by g here would be equal to 10.96 radians per second. Ooh, sorry.
No, it's blocking. It's completely blocking. The action, where the action is, the focus has to be there. So which is why I put this chair over here, so that he can sit there and comfortably he can get both the board as well as the projection. Whenever he can focus on that. Yeah.
Looking like this.
Uh,
And that side was not coming. So I told him to move backward in the same direction.
okay.
You
So,
see, this is the
so you
scope.
can't be seated at one particular location. You have to move around. So that's the work of the cameraman. And different students will have different styles of writing. So some might write this way, some might write this way. So you have to, when they write this way, you have to come this side. When they write there, you have to go there. Okay. Right? Because most of, and when the action is there, when somebody is talking, you turn that side, you're continuing to focus on the same whiteboard, nothing is happening there. Or when they're trying to explain here, you have to focus on that. Okay, wherever the action is, the camera has to move towards that.
Alrighty. Alright. So for number 4, oh, I need to erase this. So for number 4, we're given the components. We're given the components of two angular velocity vectors as a function of time. Ooh. And we're also given that the orthogonal unit vectors are in the direction of frame B. And we're asked to find angular acceleration of the object C in frame A at time t. So that was just a lot of words. To simplify this, basically we have to apply a transformation in the frame of reference, since we're currently working off of frame B, or the axes are fixed in frame B, and we're also given the transformational velocities of C in B and then B in A. So we're actually given a very handy function for how to find the angular acceleration across different frames of reference. So I'm going to write that formula down here. Alpha Oh wait, no. Okay. I think this is the formula. And so now that we have that, we can write down what we are given. So I'm going to denote our givens in blue and then underline what we have to find. So we're given, CB is given right there, omega CB. So we have omega CB equals 4t squared I plus 2tj plus 5k. And we're given that omega beta A is sine ti plus cosine tj plus 7tk. All right. And we're also given, we have to find the magnitude of the angular acceleration at time equals 1.1. So I'm just going to put that here, t equals 1.1 seconds, but we won't use that for a while. All right, and now the angular acceleration from C to B okay, that's something that we have to find. So we have to find these two values first in order to figure out this equation. This will be the final result. So alpha theta b would be the derivative d over dt of omega theta b, which would equal d over dt.
You need to mention in which frame the derivative is taken. So as a pre-superscript to the d by dt. So
it would be in the,
yeah, you can write
it would
this
be respect to
Yeah.
b, correct?
here.
Oh yes, b.
Yeah. So remember in the last class we saw it didn't matter whether we took it with respect to b or c. So whichever is convenient for you, you can take and it will still
Yeah,
work.
since it's fixed
Yeah.
in b, it makes more sense to take
Yeah,
it
sure.
from b. So, I just rewrote that. Okay. 4t squared I is 2tj. Okay. And the way I'm going to do this is because they're all in components anyways, we can just take the derivative of each individual component for its respective axis. So the derivative of 4t squared is 8t, which is just the power rule, 2j plus 0k. All right. And then doing the same thing for alpha beta A. So the derivative, oh wait. And again, this is in the B reference frame. So we can do and then that would be 7k. So now we have all of the components that we need, and we can solve through this problem. So first, we can start off by adding the two alphas because that's kind of the easy part. So just writing this out again. And now I'm going to plug in the values that we got for the two alphas. I might have to kneel for this. So 8ti plus 2j, and there's nothing on the k, plus cosine ti minus sine tj 7k. So that's the first part. And then the second part is the omega BA cross omega CB. Oh. So this right here, we can add the two I components. So that's T8, oh wait, 8t plus cosine t I plus 2 minus sine t j plus 7k. So that's the initial part, and then we're going to do the cross product here and just add it to that. So I'm just going to number this so we remember that's there. So crossing the two omegas, we have 4t squared I. I'll just do ijk here and do the cross product. So 4t squared, 2t, 5. And then we have sine t. So, sorry, I should label this omega. Oh, omega CB, omega BA. Okay. So.
Is the order switch or is it on that? Yeah, omega B coming first.
Oh, yes, my bad. Thank you. Okay. Okay. So that is the setup for cross product, so I'm just going to do this real quick. For I, we have 5 cosine t minus 14t cubed I. And then for j, it's 1 negative 5 sine t minus 28t power 4 j. I'm going to go down a line for the k component, plus 2t sine t minus 4t squared cosine t k. All right, so now that we have the cross product here, so this would be 2 in terms of t, and that's 1, and our final answer is going to be just 1 plus 2 at t equals 1.1 seconds. Right? So, yeah, so this is what we have so far. I'm just going to leave this for a sec and then erase it so we can have more space for this problem. Okay. Yeah, so now, All right, I want to take a second to plug in t into both equations now that we have it. Okay, this marker is suddenly dead. So 8 times 1.1 plus cosine 1.1 I plus 2 minus sine 1.1 j plus 7k. If someone can run that through a calculator real quick, that would be much appreciated. And then for 2, I'm just going to set this up. So 5 cosine 1.1 minus 14 1.1 cubed. Sorry, it's slightly squished at the end, but all I did is plug in the values, so there you go.
Okay, so for 1, the I components, you wrote 8.1 plus cosine 1.1, it's going to be about 9.8.
Mm-hmm.
The next part, the 2 minus sine 1.1 is about 1.98.
Mm-hmm. And then 7, 7.
Yeah.
All right.
The 5 cosine 1.1 minus 15 is
Mhm.
going to be about negative 13.6.
Mm-hmm.
J component is going to be about, it's going to be plus 4. I included minus, so it's going to be plus 4J.
Okay. All right.
Last part, it's
Mhm.
1.1 sine of
Wait.
So the last part is going to be negative 4.8.
Cool.
So you're just adding these?
Yeah. So now all we have to do is do 1 plus 2 to get the answer, and that will be negative 4.
It's about minus 3.8.
Yeah, minus 3.8, and then that's 5.98j minus 2.2k. And that should be our answer for C to A.
You want the magnitude?
And yeah, so now we need the magnitude. So all we have to do here is I'm going to erase the bottom half of this to make some room. So all we have to do is do each component squared. I'm just writing the simple version. It's not actually like the j hat squared. I'm referring to the components. And then root that should be our magnitude of angular acceleration. So I'm just going to plug these numbers into the calculator.
You get about 7.44, which is off.
Alright.
It's just some kind of calculations are off. And the process is right.
Okay, interesting.
How different is it?
It's supposed to be about 35. To do the magnitude of this, I think you get about 7.4.
I think that's a big difference.
Check.
This should have been 3.42 apparently. And that should have been 34-ish. when I solved it originally. Okay. Okay, I'm gonna run this through the calculator one more time. Sorry for the error.
Yeah, I think for the equation, the second equation, the J component, I calculated it wrong. So if
Okay.
you do it yourself, I think we get it.
All right, let me try that again. Okay. So that should be negative 40. And then because of the negative sign, that turns into a positive. Actually, I'll leave the negative for clarity's sake. It's 9. All right. So let's try that again. Okay, so it's 38 point, oh, no. $42.88. Okay. I think the K components might also be wrong.
You want someone else to help double check the calculations?
Yeah, can someone also redo the calculations with me? Thank you.
Are you in radian or degree mode?
Yeah, that's what I was just about to switch. I'm in degree mode. Should be radians.
Oh, it should be radians?
Yeah. Oops.
I feel like
All right. Let's try that again.
It is 9.25.
For the first one?
Yep.
Okay. I'll do the number 2 ones then.
if you want, you just radian.
Okay.
Okay.
Getting 1.1 equation ones.
J component?
J component, yeah, about 1.1.
Okay.
It's obviously K and 7.
You got that one right.
That one.
Alright.
All right. So that should be negative 45. Yeah. So it's minus negative 45. Wait, no, I included the minus sign, so it's positive. Negative 45.45. J. And the last one, 2 times 1.1. What? That's a very strange answer.
Is it?
It's supposed to be like, oh no, it's right. Negative 0.234, well, 235. Okay.
Okay.
And now we redo the additions.
I already did read it the first two.
Mm-hmm.
Can you take the magnitude of this?
Yes.
Nefez, what is the answer supposed to be?
So it's 35.01.
not what I'm getting.
Are you getting like 48?
Yeah.
You have your work written down, right? Can you make sure that equations 1 and 2 are right? Maybe that you just missed like some of the cross products of that.
Yeah. Oh yeah, Dr. Dinesh, feel free to jump in if you have figured out our issue, because
The coach stays away. He's not in the center of action anymore.
okay.
Did all of your cross product terms end up being 0?
Hmm?
Did all of your cross product terms end up being 0?
No, equation 2 is the cross product.
Oh,
Yeah.
that makes more sense.